All right, thanks for your patience, folks. Let's get started. So only this lecture and one more left. We're done at the end of the semester. So just as a reminder of the timeline moving forward, the final project report and presentation, both of those are due Thursday night. I was able to bump it a day, but I couldn't bump it any further than that because we have the peer reviews. And so everybody's things due strictly Thursday night at 11:59 p.m. Got to be due then so that I can then send out the anonymous assignments for the peer reviews. Then that way, at least everyone has the opportunity to do their peer reviews before the end of the regulation. So that's kind of the important thing there. So the peer reviews will be due Sunday night, but then in theory you could do them Friday, and so on. So the projects are due, the report and the presentation, upload to Canvas Thursday night, and then Friday the only thing that's due is the course evaluation sent out from the dean. So if you would like to fill out a course evaluation, those I think disappear Friday night, so make sure to do them by Friday night. Then on Sunday, the peer reviews are due, so you'll be randomly assigned a presentation and a report. So go ahead and review those, and there's instructions for how to review those on Canvas. Then there's a muddiest point, your final muddiest point, so you can reflect on the week or the whole course. Either one of those would be fine. And I think that's all that's due Sunday. I might be forgetting about something. I posted an announcement with all of these things. The final exam, then you'll have Monday, Tuesday, and Wednesday of finals week to start that final exam anytime you want. You get 125 minutes to complete it. It's a Canvas-based exam. It doesn't require respond to Lockdown browser. It doesn't require anything fancy. It's open book, it's open notes. I do ask that you complete it individually, so it's not a team-based exam, but you can complete it at home. I don't plan on being in this room during the exam period, but if you want a space to come to do it, a quiet space, just send me a note, and then I'm happy to be here, and I can send out an announcement saying that I'll be here during that exam period. But it's designed to be kind of an at-home exam. But again, if you would like this space to be available for you to take the exam during the exam period, which I think for this class it's like the 9:50 a.m. exam period or something like that, then I can do that. But the default option is it's just at home anytime you want, Monday, Tuesday, or Wednesday. You have to complete the exam before the availability window disappears. So definitely start your exam and give yourself 125 minutes in the availability window. So the format of the exam is very similar to the concept checks. If you go to the final exam module, which I've now kind of reorganized, it's at the top of the modules in Canvas. If you open that up, I've provided like a study guide. So it basically just goes through the learning outcomes for each individual unit. There's also a practice exam. It's just like a 20-question exam that randomly samples from a pool of questions that's about a third of the size of the exam. The actual final exam is about, say, 60 questions. So you get about 2 minutes per question on the actual exam. So if you want, you can take the practice exam. If you take it as many times as you like, every time you take it, you might get a slightly different set of questions. But all of the questions will be guaranteed to be over the whole units. You just might get a different set of questions for unit one the next time you take it, and so on. So the practice exam should be very, very similar to the final exam. So if you do really well in the practice exams and you feel good about all that content, then you expect to probably do well on the final exam. So not all the questions are identical between the two of them. So there might be some things that aren't quite covered on the practice exam that will be covered on the final exam, but it's a pretty good model for the final exam.
Professor?
Yep.
I think the practice exam is locked. It's locked for me and some other person, at least.
Okay, I'll double check after class, and I'll make sure that it's unlocked. So thanks for letting me know that it looks like the practice exam might be locked, but it's not intended to be. So if it remains locked for like more than an hour after class, then send me a note and remind me that it should be unlocked right now.
Okay, thanks.
Okay, so any questions about, so I see some questions on the chat. It might just be about that practice exam. Yeah, the practice exam, yeah. So, gotcha, I see what happened there. So interestingly enough, in this semester, normally when we import our Canvas shells, for some reason this semester, they didn't shift our dates automatically for us like they normally do. So we had to manually do it. And it looks like this one exam was the one that I missed. So the practice exam, I think because it was a practice, it falls in a different spot. I didn't adjust it. So it looks like it was locked May 3rd of 2020, which just meant that it was locked, at the end of the exam period, 2 years ago. So I'll adjust that date and it should be all fixed at the end of this. Any other questions about the timeline moving forward? Questions online, in the chat? Okay, great. All right, so this is a fun little unit here about kind of complex systems approaches to thinking about computation. Last time we focused on the voter model as a type of interacting particle system. So just as a reminder, last time the voter model was our example interacting particle system. Or IPS. And we primarily analyzed the voter model using stochastic modeling. So we used basically probability. So we had a probabilistic analysis making use of the dual reverse timed coalescing random walk. And that basically took advantage of ergodic Markov chain theory and Polya's recurrence theorem. And we mentioned that the voter model is a model for consensus in computing systems, as well as some people study opinion dynamics, which are social models of sort of computational properties of social systems, but it's also used to study distributed algorithms. And so, there are a bunch of consensus things. So for example, a Windows file sharing, for example, you put a bunch of Windows machines on a network. One of the first things that they do is they have to decide who keeps track of who's who on the network. And so the Samba SMB file system protocol on the network there, everybody comes in and they say, who's the leader? And they say, I have no idea who the leader is. And so they go through a process of electing a leader, and they all have to agree on who the leader is. That process can take 24 to 48 hours, which is why sometimes on at least in the old days, if you shut down the wrong Windows machine on your network, then different people would see different machines available for like 24 to 48 hours, because they'd be going through this consensus process where they had to all agree on who the leader was. And so this shows up in a lot of distributed systems as well. So it's a model for consensus, but it's also a model for genetic drift. So in other words, evolution in the absence of selective pressure with spatial constraints. And the constraints there is that there were these neighborhoods of influence. And something that I didn't say, maybe I didn't emphasize as much last time, is that those neighborhoods were translation invariant. And what that meant by that is every node in the network, or every voter, has the same shaped network. So if I borrow my opinions from these 4 individuals around me in space, if I'm in a 2D lattice, so I look left, I look right, I look up, I look down, and if those are the ones that I end up randomly borrowing their opinion of, then that star-shaped network is the same network that everybody has. And so this one here, the one next to me, is going to look at me, it's going to look at the one next to it, up and down. And so if you have that translation invariance where everybody's got the same shaped neighborhood around them, you have this interesting result where you get consensus with a dimension equal to 1 or 2, and that's with probability 1. But then you have a non-zero probability of no consensus with dimension greater than or equal to 3. So if you're embedded in a 3-dimensional lattice and you've got one of these networks, then you may not ever reach consensus. And so that's a mathematical result that we could prove, using that probabilistic analysis, using these results that we imported from thinking about ergodic Markov chains. And so that's how we analyze the voter model. It's a very mathematical approach. Today, I want to introduce a set of interacting particle systems that are really more analyzed empirically in order to sort of understand their properties. And so this is a subset of the so-called cellular automata, which I'm not referring to stochastic cellular automata. I'm just referring to good old-fashioned deterministic update rules on lattices. So these are interacting particle systems, just like the voter model, but we're focusing on where their update rules are less random. So there's sort of a deterministic way to get from one point to the other. And so these really are more like what we refer to as iterated function maps, where you start with some initial condition and then you operate on it, and then you operate on that, and so on. And then you get some possibly steady state, fixed point, or not. And so even with deterministic rules, we can find that there are certain sets of deterministic rules that display complex patterns. And so some of these deterministic rules will solve a computation. So for example, your initial condition might be a bitmap, and you want to figure out, are there more ones than zeros in this bitmap, more black spots than white spots in this bitmap? And your cellular automaton will operate on this bitmap, gradually turning it into all ones or all zeros, where it maintains the kind of density dominance throughout the whole iteration, so that by the end of it, if there were more ones to start with, there will be all ones at the end. If there are more zeros to start with, it'll be all zeros at the end. And so at the point where all the cells are equivalent, it's as if a computation just finished. It's as if an algorithm just determined that this bitmap was majority ones or majority zeros. So that's one example. Other examples is that you can actually get it to generate patterns. And those patterns might be used sort of to generate art, might be used to sort of explain novel patterns or interesting patterns you see in living systems, like the stripes on a zebra, for example, or they could be even used for things like random number generators. And so a deterministic rule generates these kind of non-trivial patterns that don't seem to repeat, and then that ends up being actually used for certain things like random number generators. And so this whole field of kind of looking at cellular automata is kind of attributed to Stanislav Ulam. And of course, as in everything else in that era in mathematics, John von Neumann. And so this is sort of like the classical ones, but who's you know, the kind of the individual that has been tied to more modern kind of investigations is Stephen Wolfram. And I'll go into what his elementary CAs are. And Wolfram wrote a book that became very popular called A New Kind of Science, which everybody just calls NKS. The same way Gödel, Bach is always called GEB, the New Kind of Science is always called NKS. And this sort of, you know, outlines this idea that, you know, Wolfram was a physicist and a little bit of a mathematician. And so, you know, Wolfram's ideas were that rather than looking to the natural world for our empirical systems, there's actually a way to look at empirical systems which are mathematical in their nature, their fundamental nature. And rather than writing proofs about them, we can explore them empirically, and we'll find that there'll be interesting patterns that will raise new questions, and answering those questions may provide answers that are actually useful back in the real world. And so that was kind of the manifesto that he was giving in this kind of a new kind of science, this book that he wrote that that was sort of focused all on these cellular automata, these ECAs. All right, so that's enough intro. So let's look at you know, these CAs. And so I am going to, so what do I mean by cellular automata? So it might be easiest for me to just talk about these elementary CAs. Or ECAs. And elementary CAs are one-dimensional CAs where the update rules are deterministic and only depend on a cell state and its two immediate neighbors. So I can start out with some initial state, and it's just going to be a line. And I, for simplicity, am going to assume periodic boundary conditions. So I'll just write this here, periodic boundaries. Which basically means that the cell here has its neighbor is immediately next to it, but it's also over here. So this cell's neighbors are the ones that are kind of highlighted here. They're to the right and then way on the other side. So it's as if this is a tape that is rolled over on top of itself to form a ring. And so you've got all of these cells, and in an ECA, these cells take the value of 0 or 1. So I guess I should make a note of that here. Cells take values from 0 or 1. So they're binary. So I might have some initial conditions that look like this. You know, there's later on something else down here, maybe they're all ones, whatever. So there's some initial condition. And the rules, we can think about the neighborhood for these rules as these little triplets and the output from these triplets. And so usually for an ECA rule, we depict them as a little triplet here. Looks like a little Tetris piece. where you can view these as the inputs, this as the output, where we've got our focal cell here. So I'll just write focal, or I'll try to write focal. I'll just say, I'll call this cell, and then I'll call this left and right. So the idea here is that this little t allows us to say that, or if I were to write, maybe this is our focal cell, F-O-C-A-L, this is its new value. So by writing the rule in this lookup table in this way, then it allows me to say, given a particular state of my focal cell and its neighbor to the left and its neighbor to the right, this is going to be the value of the focal cell in the next step. So let's say I wanted to write rule 44, and I'll tell you why it's called 44 in just a second. In rule 44, I might write that as 1110 for this part of the rule. So I'm going to write, these little, each one of these here is one of these things here. So I'm going to write 8 of these things down here, representing the 8 different inputs that are possible. So we could say that in this particular case, when the focal cell is a 1, and it's surrounded by a 1 and a 1, in the next iteration of the cellular automaton, it's going to be a 0. So then I could say, well, what about in the next case? Well, in this case here, if it's a 1, 1, 0, then we're saying when the focal cell is a 1, its left partner is a 1, but its right is a 0, then we're going to also put a 0. And I can keep doing that. So I'll go down through the 8 possibilities here. I'll maybe try to switch colors to make it clear. Trying to fit all 8 here. 1, 1. I know I'm just counting down in binary, but I am notoriously bad at at avoiding mistakes when I'm in front of people. So, so let's make sure that I got all 8 of those. So this is binary 0, 1, 2, 3, 4, 5, 6, 7. So there's my 8 options for 3 bits. And then each one of those outputs here. So for 101, I'll put 1. For 100, I'll put 0. For 011, I'll put a 1. For 010, I'll also put a 1. For 001, I'll put a 0. And for 000, I'll put a 0. And so this is the way we could write the rules with all of these little triplets. Or if we know that we're always going to order them in this sort of binary order, where we're going to say that in the state, in the kind of input state of 111, it's a 0, and 110. If we're going to sort the input states like their binary digits here from 7 down to 0, we can actually get rid of that and summarize the entire rule with an 8-bit string, 0010 1100. And so this this string, this here, if I were to think about this in terms of so this, if I was thinking about this in terms of hexadecimal, then this would be a hexadecimal digit 2, and this would be the hexadecimal digit C. So, or in other words, this is 2 in decimal, and this here is C, ABC, 10, 11, 12, so 12. think I did that right. So this rule together, this number, this 8-bit binary digit is going to be 2 times 16 plus 12, which is going to be 32 plus 12, which is going to be equal to decimal 44. So these rules in ECA, this is ECA speak here, are named by the decimal version of their binary encoding for the rules. So if you were to write the 8 steps in the lookup table down as a binary string and then convert that binary string to decimal, you get the rule number. Now my background's in electrical engineering. We don't talk in decimal in electrical engineering, we talk in hex. And so it makes a lot more sense to me for this to be called rule 2C, because in hex, each hex digit is a nibble, it's 4 bits. So it's very quick if I just remember, and I'm a little rusty because I don't work in an electrical engineering department anymore, but back when I wanted to do a lot of EE every day, then you memorized all 16 hex digits and which nibble they corresponded to. So if you said rule 2C, you could very quickly know that, well, 2 is 0010, C is 1100, you line them all up together, and then you could visualize the rule. But Wolfram was not an electrical engineer, he was a physicist. So he came up with the convention that we'll just name them decimal, even though it's totally non-functional. So when you say rule 44, you're like, what the hell is rule 44? You have to convert it to a binary string in order to get sort of any intuition. Once you write it out in binary, you get some intuition because you can see that, if the left bit is 0, we just copy the cell. That's what's happening down here in this nibble, is that whenever the left digit is 0, we ignore the right digit and just copy down. But when the left digit is 1, then it's a little more complicated. Then we only get an output 1 when the right digit is also 1. So that's kind of a way you can interpret these things, is that once you see the binary here, you can start looking for logical patterns among the digits and then try to infer what they do. So this is rule 44, and if you like to see what they do, let's just see rule 44 simulated. So I'm going to hop over, and rather than writing like a MATLAB script to do this, what I'm going to do is I'm going to open up a program called a NetLogo, which is an agent-based modeling tool. It's very popular in the social sciences and life sciences. And if you search for NetLogo, they actually now have a web version. So it is a desktop version you can download, install. It can do multi-processor stuff. So if you want to run a bunch of simulations across a bunch of cores, you can do it very quickly. But if you just want to demonstrate something to someone else, it can actually generate a JavaScript version of all of NetLogo and put your model into it so that you can then export your model to a web browser for someone else to use your model. And so they have a bunch of samples in there. So I'm just going to go into NetLogo web here. And an agent-based modeling tool allows you to set up rules for a bunch of mobile agents as well as a bunch of immobile patches. And agents run around a world crossing over patches, and they can bump into each other and interact with each other, or they can interact with other patches. So linking this kind of back to stuff we've done earlier, if I search for optimization, they have an implementation of particle swarm optimization. What they've done is inside this NetLogo here, if I hit setup, notice there are these parameters up here, landscape smoothness, and then don't worry about population size. Population size are the number of particles. But this landscape smoothness, they basically create a type of landscape. And so there are these things like NK landscapes and there are a bunch of these routines that allow you to create randomized landscapes that have certain coarse grained properties. And so you can adjust this smoothness parameter to create these landscapes that are different levels of hills. Like they might have one big hill or they have a bunch of small hills. And so this created something that it's a heat map here where sort of the brighter regions are higher and the darker regions are lower. And the very highest peak on here has height 1. They just normalized it. and then they create 50 particles, and then they implement particle swarm optimization. So if we look down here, they've got particle inertia. So that's that inertia pattern or a parameter we have. They have a particle speed limit. I mentioned you can put a speed limit on particles, although I didn't show you it in the algorithm. And then they've got attraction to personal best, and they've got attraction to global best. So I can crank these all the way down to 0 and hit go. And what I'm going to see is that these particles basically do, they're going to basically travel mostly in straight lines and slow down. And that's because they don't have any attraction to anyone else. And so they just kind of run out of energy, and the update rule brings their velocity down to 0. And so they slow down, and it shows me the best that they found in this case is 0.9466. Now, if I crank their attraction to personal best up to something maybe not that high, maybe a little bit higher here, then they start moving again. And notice they just kind of like, well, they end up finding the best. So let me reset up and hit go again from a fresh initial conditions. And notice they just kind of wiggle around the same spot here. So this kind of gives me an intuition that if you have no attraction to global best, then what your particles do is they find the best in their local history, and they just can't quite get away from it, because as they move away from it, they turn around and they come right back to their personal best, and they end up kind of settling out in these spots here. Now, if I do attraction, if I crank the attraction of personal best down to 0 and the global best up to very high, then you see them all trying to find each other. The updates maybe are a little slow on Zoom here, but they kind of turn into this gnat swarm where they all want to go in the same spot here, and they end up finding the best value. So by playing with this agent-based model, I get kind of a way to experiment with what these different parameters do. And I can see that there's this trade-off where if I have them both being attracted to their personal best and their global best, then maybe I can actually get them to do the right mix of exploration and exploitation to end up finding the best value. And so, yeah, so this is just, this isn't a lecture about particle swarm optimization, but it's just showing that this is an example to explore empirically how particle swarm optimization works using these agent-based modeling tools. Now, the reason I bring this up is the other sort of sample model that they have is they have several cellular automata models, including the one-dimensional elementary CA. So I can load the 1D CA, and if I hit this down here, it says rule switches, rule 105. Well, I can change this to rule 44, and if I hit set up single, yeah, there. So, and then notice when I did rule 44, it updated these bits. So 111 gives me a 0, 101 gives me a 1, 011 gives me that, and so on. And so we can see that when the most significant bit is 0, it just copies the bit. When the most significant bit is 1, it has this more complicated logic. And I can either say set up single, where it's going to have, it might be really hard to see, but there's a single white dot there. So if I just hit go, we can see what happens here. So in this simple rule, every row is an iteration of the algorithm. So you initialize the top row with a bunch of zeros and a single 1, and then a bunch of zeros. Well, we know that when the left neighbor is a 0, then it just copies whatever the central cell is. And so it makes sense that this is just going to copy all the way down. So if I hit go, it's just going to be a straight line. So the iterative function map, it sort of reached a fixed point. Now, if I do set up random and have it go, then we can see potentially a few more interesting things happening here. So you can see that it did a random initial condition there, and there were some transients, but eventually it found this fixed point where it just, this bit string here doesn't really do anything that exciting. So rule 44 isn't that exciting. Now there are other rules, like I can drag this up to rule 110, or I can type it in if this gets too frustrating. There we go. And if I do set up single on rule 110, then I get this pattern. So, so here, this is, again, it's just using simple rules like this, but it's a different set of rules. And when you initialize it with a bunch of zeros and a 1 in the middle, you get this cool triangular thing going on here with rule 110. Now, if I do set up random and then hit go, then I get kind of a similar set of thing with this triangle, but then the triangles kind of interact with each other. So you notice that like there's sort of a growth in these big triangles, but then suddenly these little triangles show up and they kind of bounce back in the other way. And you know, I think this just kind of looks like an interesting pattern, kind of looks like maybe reptilian scales or something like that. But the crazy thing about rule 110 is that it's Turing complete. What that means is if you have an infinitely wide cellular automata, there's a way to take any computable program and encode it in the first row and then hit run. And that program will actually, there's a way to then read off the calculation. So you can actually tell when this thing settled out and completed the computation and read out the computation. So let's say you've got a for loop that adds up all numbers from 1 to 100. There's a way to encode that for loop as the initial condition to rule 110. You're going to need a really long cellular automata. It's going to be really, really wide, but there is a way to actually to program rule 110 so that it will then compute that for loop. And so you'll hit go, and then there is a way to read out the output of this to actually see what the sum of those numbers are from 1 to 100 or whatever in your for loop that was keeping adding those up. So that's an example that, you know, is one of these things that initially I think, you know, Wolfram looked at all of these rules and he found certain sets of rules, like he actually categorized them into different categories. So there's really boring rules like rule 44, and then there are these kind of really complex rules like rule 110. And then these, you know, then when he started looking into the complex rules, that's when he figured out that actually there's a way to program rule 110 to solve any computable program. It is Turing complete so long as you have infinite space. And so what's kind of neat about that is if you think about what's going on with these rules, rule 110. So if I go back to the notes here. So if I'll just write that down here. So ECA rule 110 is Turing complete. And so, and that's not supposed to be there. And so if I think about that, what really is the CA doing? Well, the CA is really not doing anything different than a recurrent neural network or a time-delayed neural network. So if you think about rule 110, I've got, you know, each one of these cells, and if I just draw them in vertical instead of horizontal, then the cell's next state is going to depend upon its current state as well as the state of those immediately around it. And so this cell, you know, it depends upon its current state as well as the states around it. And that's what generates the next iteration. Well, this really is just no different than a recurrent neural network. In other words, I could implement a cellular automaton as a recurrent neural network. So if rule 110 is Turing complete, then so are artificial neural networks, so are recurrent neural networks, as long as you've got enough units. So in principle, you can take a recurrent neural network with a layer, you know, is infinitely wide, and you can have it compute any computable function. And that's something that maybe we learned that might not have been as obvious when looking at the neural networks, but when we visualize them as elementary cellular automata, then it starts making that more clear. Okay, so let me pause there. So are there any questions about about this basic idea. An elementary cellular automata, rule 110, Turing completeness, etc. Let me make sure there's no chat messages, and let me get rid of this. Subtitle. Okay. So that pretty clear. All right, so so these are one-dimensional CAs, and I'll show you a couple more either that have some interesting properties either today at the end of class here or next time. But I also want to mention that you don't so the ECAs are kind of the simple case, these 1Ds, but there's also plenty of 2D CAs as well. So there's two-dimensional CAs, which are deterministic as well, but instead of having a neighborhood that's based on just the immediate neighbors left and right, you can create CAs where you have a focal cell, and then it's got a bigger set of neighbors. And so that focal cell's next state depends upon neighbors around it. So all the way around it, as well as itself. And there are some famous examples of 2D CAs, like John Conway, who died not so long ago. Conway's Life. So back in when I was first learning software engineering and things like that, everybody had Life as a screensaver. And so Life was an example, and I think I've got I'm sure they've got Life here in NetLogo. Yeah, there we go, Life. And so Conway, this is a 2D CA. So now what's going to happen here is if I do say setup random, it randomly initializes different spots with ones or zeros, black or white. And then it has this rule set, which I think they probably have the rules, not in, I don't want to go to code in the model info. The rules here is that under how it works, each cell checks the state of itself and its 8 surrounding neighbors, and then sets itself to either alive or dead. If there are less than 2 alive neighbors, it dies. If there are more than 3 alive neighbors, it dies. If there are 2 alive neighbors, it remains in the state that it is in. If there are exactly 3 alive neighbors, the cell becomes alive. This is done in parallel and continues forever. So basically, it's sort of like if you have too few neighbors, there's not enough of a sort of a social system and you die. If you have too many, everybody's over competing for and you die. If you're dead, but there's enough neighbors around you, then you're sort of modeling reproduction. You then become alive as an offspring. And that kind of process goes on. So that was kind of Langton's idea of something that he wasn't trying to mimic life, but he was saying, what would sort of artificial life maybe look like? And if I then say go forever here, then what happens here is you get these patterns that show up. So if I pause here, there are certain things called pills, which are fixed points, like local fixed points. They, as long as nothing collides into them, they'll stay there forever. But then you also get these sliders that you can maybe start seeing walking across here. Trying to see, like, yeah, okay, so there's some that are sort of happening around here. That there'll be these little shapes that kind of walk and they maintain, like here, there's kind of a slider that goes on here. Maybe if I hit setup random again, I'll get a few more sliders. And so you can kind of see sometimes these sliders are generated, which kind of slide across here. And you can also get these sort of oscillating patterns where you can have these 2 sort of fixed regions that shoot at each other, kind of back and forth. So it was just kind of so what we like, like I said, back in the day, we would have screensavers that would just initialize life randomly, and they would just run in the background, and you get different patterns every time you ran the screensaver. So it'd be this sort of this generation of new complexity. Sometimes they would get kind of boring, and if it ever reached a fixed point, it would regenerate itself. But otherwise, if it kept moving, then you get sort of a new pattern. As you came back 10 minutes later, it'd be a totally new pattern. But they were just being driven by these deterministic rules. And so this, in these 2D CAs, we're looking at each iteration. We're not looking at the history of them like they're in the 1D CAs. And people sort of did try to think about applying these in natural systems. So if I look up Brian's brain, for example, so in Brian's brain, this is an example CA where the cells actually take on 3 states. They can be active, inactive, and this, if you remember when I talked about action potentials and neurons, a neuron can be kind of quiescent, not active, it can be active. And then there's a refractory period right after it's active where it doesn't respond to stimuli. It's sort of an in-between state. So if you're inactive and you get stimulated, you'll become active. If you're active and get stimulated, well, you're already active, but you're in the refractory period, you kind of ignore any stimuli. And so in Brian's brain, he kind of set up a similar sort of rule where you had these active and inactive and refractory states, and you get these sort of, the red, I think, is the refractory ones here. And so you get these sort of interesting patterns, kind of lifelike. But the reason it's called Brian's brain was he's saying, like, what can I build, like a simple, like a minimal working model of kind of a spiking neural network? And this was sort of his attempt at that, is to say that I've got a bunch of cells that pay attention to the cells immediately next to them. When the cells next to them get activated, it tends to stimulate this cell, but this cell stays active for a short period of time and then goes inactive and starts ignoring the cells next to it for a small refractory period, and you get these patterns. And the suggestion was that some of the patterns that you see across the cortex might be modeled in the same sort of way. And so if you've got neurons in the cortex that are responding to stimulation patterns of neurons around them, you might get these wave fronts that go across the brain that might actually be explained by a 2D CA, something like this. It's kind of what we're kind of getting at here. So a lot of interesting complexity comes out of totally deterministic rules that just have random initial conditions. And that's Brian's brain as an example of that. All right, so questions about that? All right, so I mentioned earlier, questions online, any questions in the chat? So I mentioned earlier that it's possible to do computations, potentially useful computations with CAs. And it shows you an example of how computation can be embodied in physical space. So if you have a bunch of computational agents that are responding to themselves and the environment around them, then maybe you can actually see a computation unroll in physical space. And one example of that is density classification. And so this is sort of a common model system for thinking about CAs. And I already kind of talked about this already. You can imagine you have an initial condition. So this is my initial row. And you can think of it as like maybe cells of a bitmap that have just been smashed into a line. And we want to generate, use ECA rules so that when this thing reaches a fixed point, then if all ones means that it was majority ones in initial condition and all zeros is majority zeros in the initial condition. And so in this example here, you might hope that there'd be one ECA rule that could do density classification, but it turns out that there's not one ECA rule that's perfect at doing density classification, but you can combine two of them and you actually do a pretty good job. And so if you start with rule 184, which is also known as the traffic rule for reasons that I will explain either today or next time. And then you run rule 84 for a while until the transients die out. And it's like a pre-processing step. It's like almost a feature extraction step. It kind of gets your inputs ready for the real killer, which is rule 232, which is the majority rule. Now, again, the decimal encoding just bothers me every time I write it down. Like, you think like, why is 184 the traffic rule? If I were to write 184 out, you would see exactly why it was the traffic rule immediately. But as a decimal, it's like, I can't see, how does that relate to traffic? Likewise, majority rule 232, where is the majority there? Now you can imagine what majority rule might be. Like that's probably going to look at the 3 bits that's in the input, and then based on the majority ones or zeros, that's going to be the output. That's why majority rule kind of makes sense. If we encoded that in hex or in binary, we might actually be able to see that right out of the rule name. But as decimal, it's just so stupid. But that's the convention, just to use decimal. So 184 and 232, traffic rule, majority rule. If I do those, so I'm going to go back to my ECA simulation here. So look back up Cellular Automata, 1D ECAs. And I'm going to start with the traffic rule, rule 184. So 184. And I'm going to just set up a random set across the top. Now that, I think, this has a random density of 10%. So let's just, I don't know why it'd be more interesting. I'm going to make it 89%. So I set up random, you see it's mostly green up there. Now, if I hit go with 184, then now you might start seeing why it's called the traffic rule. It actually starts looking like a traffic pattern. What's actually happening here is that initial condition, it ended up sort of, you can think of them as cars driving, and or you can think of gaps in between cars that you might be seeing here. So as the cars are moving one direction, the gaps are moving backwards. And so the traffic rule. So there was sort of, and it's hard to see, but if you look right above my finger, there's a transient, like in the first couple of rows that got resolved. Otherwise, then it becomes this kind of steady state pattern where they're just moving around. Well, now that the transient has died out, I can flip to rule 232. Almost got it in one shot. Let me just type it in. And now, if I hit go with 232, which I think it should, yeah, it should, it looks like it, yeah, okay, there. So right, I forgot how to do this. So it's, whenever you hit go, it latches in that. So the top there, that is the outcome of the traffic rule. And now this is the outcome of rule 232. So basically, letting the transients die out of the first rule sets up the initial conditions so that when you do the majority rule, rule 232, it then finishes up. And so when this guy turns all green, that means that I started with a density that was more than 50% green. So if I were to go back to this, set this to say, density 21%, so now it's less than 50%. If I go back to my traffic rule, which I always forget, 184. So maybe slide this back. Let's type it in. I will try to type it in. sorry, 184, okay. So now I'm gonna hit go. And as you can see, this pattern is very different than the initial pattern. It might be really hard to see it, but the initial pattern's got like a spike there, a spike there, a spike there, a spike there. It does not have it. So the traffic rule turned that initial pattern into this pattern. Now that I've got this pattern, I can flip to rule 232. Right there. And if I were to hit go now, then that 232, and I'm not sure why it's, unless I got my rule wrong. So 184, this is live TV. All right, so there's 184, that's the traffic rule. That makes more sense of the traffic rule. If I then now set it to 232, and I'll wait for it to, there we go. That's what I was aiming for there. So it restarted. I had to hit auto continue for this to work, but and now it's continuing to auto continue, so it disappeared. But the traffic rule set up those diagonal lines. And once those diagonal lines kind of spread out that density just right, then the majority rule was able to pick back up off of it, and it turned it into all black. So combining those two rules together allowed us to do density classification. Now it turns out that you can actually build CAs to do even more complicated things like pattern recognition. So you can actually build a CA to recognize letters. So you can say like, actually to do classification. So based on, you can have a two-dimensional CA that actually is able to classify vowels. And so you can have it run and it will turn all green if it recognizes a vowel and all black if it recognizes a consonant. So it's an example of kind of this distributed computation where each cell is only able to keep a little bit of memory of what its current state is, and it's able to query the memory of a limited number of cells around it. But by adjusting those rules, you're able to do this classification. And that should make sense because that's basically what you're training a neural network to do. But this is sort of a visualization of kind of a spatially embodied neural network. That's really what these CAs are doing. Now, with that in mind, you might say, well, how do I build such a CA that does that classification? Well, in neural networks, we have optimization algorithms to do that. So we have, loss functions and gradient descent and so on and so forth. And there are a set of similar methods for designing CAs. So like this project EVCA, which is like evolving cellular automata, if I remember correctly, which I think I've got some links to on the Canvas site. These are efforts to use genetic algorithms to evolve CA rules or combinations of rules to accomplish difficult computational tasks. And so you can think of this like back propagation for CAs, but instead of using gradient descent, but GA instead of gradient descent. So for whatever reason, we really got excited about neural networks early and neural networks to become this big thing. But you could imagine an alternate universe where, for whatever reason, CAs really caught on, and CAs became the dominant sort of machine learning paradigm, and things like EVCAs and things like that might have become the tools that were recognized as like backprops right now. But in this universe, neural networks were dominant, but really CAs aren't that different than neural networks. They just have this more of a spatial component, and they're maybe easier to visualize. Arguably, maybe you could have had more explainable artificial intelligence if artificial intelligence was built on top of CAs than neural networks, because whereas in neural networks, we try to make sense of these latent variables and what do they all mean and whatever. But when you have something that you can visualize in space, you start seeing that, well, maybe I don't need to have a meaning for the latent variables. Maybe these pills and sliders that evolve across the CA, maybe those are the things that I need to actually give citizenship in my theoretical models. And there are people that do that. There are people that build thermodynamical models of CAs where they start sort of trying to understand, what are the properties of these sliders and things like that, and can I coarse grain them so that I can actually, instead of worrying about the CA rules, can I think about the rules of the slider? So can I make a coarse-grained model of the slider where the slider is the object which is sliding around, not the cells making up the slider? And there are a bunch of people doing work on that. And some of the cool things that come out of work like that is things like studying reversibility and irreversibility. So I think NetLogo's got an example of a reversible CA here. So elementary, continuous, turtle-based. I've got all these sample rules. I think totalistic is the model that I'm looking for. Let me just double check. No, I don't think this is it. So I thought it was right under like reversible CAs, and but no, this isn't the one that I'm looking for here. I really thought that the last time I looked in here, there was a reversible CA that was immediately available. But one of the interesting things about CAs is that there are classes of CAs that we refer to as reversible CAs, which basically mean that you don't lose any information as you go from one step to the next. In other words, every rule that brings you to the next iteration can be undone. So you can actually go backwards as easy as you go forward. So every state has a unique path to the previous state. And you might think that every such reversible CA would be doomed to produce boring patterns, because if you sort of have to keep your entire history stored in a single row, the rows got kind of limited memory, and so only boring histories could kind of be available to you. So like the traffic model, well, it's easy to sort of see that the traffic model might be reversible, because as a cell moves to the left, you know that, well, it could only move to the left, and so if I reverse, then it goes to the right. And but the traffic rule is kind of boring. But it turns out that there's a wide range of reversible CAs that end up generating what look like white noise. So they start out looking like something that like a text of Shakespeare or something, or a pretty face or something like that. And when you run them and they look like white noise, and you think, oh, well, that's definitely can't be reversible. But then you can hit reverse, and it will go back and reverse every single step right back down to the original initial condition, that face there. And that was sort of an interesting thing that kind of came out of it. And it kind of gave us, it made us think about, entropy and all things like those are examples where from our perspective as humans looking at it, it looks like entropy is increasing, but in reality, if you knew the state of every single particle, the entropy was staying flat. And so a lot of really interesting insights have come out of people looking at using these CA models. And now there are people thinking about CAs for computation, but they're largely viewed in this kind of new kind of science way as a model entity for us to explore complexity without ever having to build a real system with these real rules. And so we know what the rules are inside of CA. We can see what complex patterns come out of CA, and we can hopefully understand where those patterns come from. So those are elementary CAs, and a couple of examples of 2D CAs and 3D CAs. Where I want to go to last, on Thursday's lecture, is to mention a couple of extensions of CAs, like stochastic CAs, and also I want to bring it back to thinking about evolutionary systems. I mentioned that there are folks like this, like Melanie Mitchell and some others that have been looking at, how do you evolve CAs that do interesting things? Well, once you mash up evolution and CAs, then you can start thinking kind of the other way around. It kind of almost brings us back to the voter model. You can say, what if evolution happened on a cellular automata? So what if we had a distributed GA where every cell has a GA running on it, and it's exporting individuals to the cells around it according to kind of a CA-like rule. So just like you can use evolution to build CA rules, you can actually use CA rules to set up metapopulation dynamics for GAs. And that's kind of another way that things are brought together. And that's something else that I kind of want to close on next time, so that you have some familiarity with these sort of spatially coupled distributed GAs. But that's all I got for you today. No use for me blabbing on farther than that. Any questions or comments? Questions about the final exam for anybody came in late? I don't see any other questions online. If not, then we've got our last class on Thursday. So again, the course evaluations due Friday. The project, both the presentation and the report, due Thursday. And that's all I've got for you. So we'll see you Thursday, and good luck on the projects. So any other questions online? If not, I'll go ahead and stop the recording.